Hello everyone, I'm Samarth and today I'll be talking about our work on a unified approach to translate classical bandit algorithms to structured bandits. This is a joint work with Shreyas Chaudhary, Subhajyoti Mukherjee, Gauri Joshi and Osman Yan. The full paper is available on arXiv. Let's get started with a quick discussion on classical multi-arm bandits. In the classical multi-arm bandit problem, a player is faced with k arms. At each round, the player picks one of the k arm and receives a random reward corresponding to that arm. Each arm has a different reward distribution, which is not known to the player. The goal of the player here is to maximize the cumulative reward across a total of t rounds. The goal of maximizing cumulative reward is in turn equivalent to minimizing cumulative regret. The regret could be thought of as the loss incurred upon pulling the suboptimal arms. The multi-arm bandit problem formulation has been proven to be useful in several application settings. One such setting is the recommendation systems, where you want to decide which movie to advertise to a population. These movies could be thought of as the arms in the bandit problem. At each time step, a user comes in and you show one of the movie ads to a user and receive a reward in the form of a click or the time that the user spends on the system. The goal here is to maximize the cumulative reward by sequentially recommending available movies to entering users. Several exploration exploitation algorithms are known for the multi-arm bandit setting. Some of the popular ones are UCB, Thompson sampling, and KLUCB. These algorithms are online in nature and ensure that each of the k-1 suboptimal arms are only pulled order of log t times in a total of t rounds. And hence, we have a regret that scales logarithmically in t. In turn, there are lower bounds showing that the regret cannot be improved further upon. The classical multi-arm bandit setting implicitly assumes that the reward corresponding to different arms are independent. However, if you consider the example of advertising, the rewards are likely to be dependent because movies of similar genre or cast might generate similar rewards. Motivated by this, people have studied several variants of the multi-arm bandit problem. One such variant, which is very popular for the ad recommendation problem, is the contextual bandit problem. In the contextual bandit problem, the goal is to provide personalized recommendation. A user comes in and the player is allowed to see their contextual features, such as the age, income, occupation, etc. Based on these features, the contextual bandit algorithms try to recommend a movie which is well suited to their context features theta. So in a way, it tries to learn a mapping between context features and the arm that they will like the most. The mapping between contextual features and the expected reward for different movies is not known here. In contrast to contextual bandits, we study a multi-arm bandit setting where the contextual information of the user is unknown. However, we know how different type of users react to different type of movies. For example, a child is likely to enjoy the Disney movie Aladdin, whereas it is unlikely that the movie Joker will appeal to a small kid. One might wonder how these reward mappings are known in practice. These could be known through one, controlled user studies for different type of users, or two, from information recorded from a previous advertising campaign. Formalizing this into a framework, we have the unknown contextual features of the user theta star, but the mapping between different type of user and their preference is known through the mean reward functions mu k of theta. In our study, we place no restrictions on the type of these functions, and the goal is to maximize cumulative reward. Let's understand the framework better through an example. Suppose we have a simple scenario where we have an unknown theta star that could take any value between 0 and 6, and the mean reward functions are known in the form of mu1 of theta, mu2 of theta, and mu3 of theta. Let's say the hidden parameter was 3. In this case, if we show arm 1, we'll receive a random reward with mean 2.5. The structured bandit problem studied in this paper has been looked separately in several different papers previously. For example, the Work on linear bandits consider a setting where the mean reward functions are of the form of WK transpose theta. Similarly, the generalized linear band framework studies a setting where mean reward mappings are of the form of G of W transpose theta, where the function G is invertible. More recently, global and regional bandits were studied, which assumed that the functions μk of theta are invertible. In our work, we force no restrictions on the mean reward mappings. These mappings need not be invertible or linear. They can be arbitrary functions of theta. Moreover, theta can be a vector as well. This is the key difference in our paper when compared to GLM, linear, global, and regional bandits. A work close to ours is the work of Combs, but that assumes that the conditional reward distributions are known and requires the algorithms to solve a computationally intensive optimization problem in each step of the algorithm. The work closest to us is the work of Latimore done in 2014, which proposes an extension of UCB to the structured bandit setting. Our work in this paper extends not just UCB, but any classical bandit algorithm to the structured bandit set, a problem that was left open to be solved by Latimore in 2014. So let's go over the key ingredients of our proposed approach. To tackle this problem of structured bandits, we have a three-step procedure. In the first step, we identify a confidence set theta star based on the observations recorded so far. Next, we remove some seemingly suboptimal arms for the tth round. And then amongst the rest, we use a classical bandit algorithm to recommend one of the arms. Let's see these steps better through an example. At round T, we have an empirical estimate on the mean reward of each of the three arms, and we also know how many times each arm was pulled till round T. Using this, we can construct a confidence interval within which the mean of arm 2 lies with high probability. This can then be mapped back to construct a confidence interval theta star. In this case, we see that theta star is likely to be in 1.5 and 4.5 at round T. Now we know that with high probability, theta star lies in 1.5 and 4.5. After knowing that theta star lies in 1.5 and 4.5, we see that arm 3 cannot be the optimal arm as it has low mean rewards for all theta star in 1.5 and 4.5. So it seems unnecessary to explore arm 3 at this point, and we call it non-competitive and remove it from the candidate set of arms at round T. We call the remaining two arms at round T as the set of competitive arms, as both of these show promise and need to be explored. So in the last step of the algorithm, we employ a standard bandit algorithm such as UCB or Thompson sampling to make a selection among these two. This completes our description of the algorithm, which first constructs a confidence set for theta and then eliminates some empirically non-competitive arms and chooses an arm from the remaining set of competitive arms. Because we are doing this elimination in step 2, we have nice theoretical guarantees for the algorithm. Before we go there, let's understand what are the competitive and non-competitive arms. So if we repeat the previously described process, we'll end up pulling the optimal arm K star infinitely many times. And if theta star is the confidence set obtained by after pulling the optimal arm infinitely many times, then we call an arm competitive if it is theta star non-competitive. That is, for all values and theta star, arm K is suboptimal. The number of competitive arm depends on the confidence set theta star, which is in turn dependent on the hidden parameter theta. Therefore, the number of competitive arms varies with the value of hidden parameter as shown in this particular example. When theta is between 2.2 and 4.8, the number of competitive arms are 2 and it is 1 otherwise. Our regret analysis shows that the expected number of pulls for a non-competitive arms are bounded, whereas the pulls for competitive arms are of the order of log t. As a result of that, the regret of our proposed UCB-C algorithm scales as c minus 1 times order of log t, and in fact, when c is equal to 1, our proposed algorithm achieves a boundary regret. If one discarded the structure in the algorithm or the elimination step, then each suboptimal arm is explored order of log t times in a total of t rounds by algorithms such as UCB or Thompson sampling. In our algorithm, because we eliminate some arms to exploit the structure, we see that only some of the suboptimal arms are pulled order of log t times, whereas the others are pulled order of 1 times. The number of suboptimal arms that are played order of log t times varies, which we call C, and it varies with the problem setting. For instance, we can have scenarios where C is 0, 1, and 2 for a 3-armed bandit problem. For example, if we have this example with the mean reward mapping shown at the top, and we could have 3 different scenarios, and in each case, our proposed UCB-C algorithm and TSC algorithms, which use UCB and Thompson sampling in the last step of their approach, achieve lower cumulative regret than UCB. In fact, when C is 0, our proposed algorithm achieves order 1 regret as illustrated in the first subfigure. To validate our findings, we did experiments on a real-world recommendation dataset. We took the MovieLens dataset and used a part of the dataset to learn mean reward mappings and ran the algorithm on the remaining dataset. The goal was to find the right movie genre for an unknown user while incurring minimal regret. We saw that even in such real-world scenarios, our algorithms were able to exploit structure, eliminate a large number of arms in step 2 itself, and achieve a regret much smaller than the standard approaches. To summarize, the structured bandit framework allows us to provide recommendation without knowing contextual information a priori. As only some of the suboptimal arms are pulled order of log t times, and non-competitive arms are pulled only order of 1 times, we get a regret that scales as c minus 1 times log t instead of k minus 1 times log t, where c is the number of competitive arms. In fact, when c is equal to 1, our proposed algorithms achieve bounded regret. Our approach allows us to extend any classical bandit algorithm to the structured setting by plugging the algorithm into step 3 of our proposed methodology. In future, there are several open directions, such as considering the best arm identification problem in the structured bandit setting, where the goal is to identify the best arm in as few samples as possible, or to improve the existing algorithms by making use of the arms that help us estimate theta better. Thanks for attending the talk. I hope you liked it.